So in this video, we're taking a look at integrals and derivatives with the fundamental theorem of calculus. Okay, so we've got three objectives we're going to look at. Use the fundamental theorem to find the derivative of an integral function. Use the chain rule as a part of this. And then the last piece is using the fundamental theorem when we have two variables of limits of integration. So let's take a look at this slide and just kind of read through a couple of highlights here. If you take a look at this first piece right here, the fundamental theorem gives us a way to evaluate definite integrals without using Riemann sums or calculating areas. Okay, so that's really the focus of what we're doing. Excuse me, I have a hiccup. So it gives us a way to evaluate definite integrals without using Riemann sums. There are two parts. We talked about part 2 earlier in the previous section. So in this case, we're looking at the first part of this fundamental theorem of calculus. It establishes the relationship between differentiation and integration. Okay, so what we do is we say if lowercase f of x is continuous and the function f of x is defined by this thing. Okay, so the way this is set up is a little off. If f of x is defined as this, then the derivative of f of x is equal to the lowercase f of x over the entire interval. So really and truly, this is just a weird way. This is the mathematician's way of saying the derivative cancels. Now look, this is Mr. Stark terminology. This would get you in trouble with a pure mathematician. So I'm just trying to talk to you the way I would want somebody to talk to me. The derivative cancels the antiderivative or the integral. Okay, so if I asked you to take the derivative of an integral, basically it cancels. Much like a square root is canceled by a square, right? So these things cancel out. This one says, use the fundamental theorem of calculus, part 1, to find the derivative of this guy right here. Well, the truth of the matter is that the derivative and the antiderivative cancel. And so if I said find g prime of x is going to be 2 over, now notice there's a slight change right here, not t anymore, x. So we're going to take this thing and plug it in for all the t's that we have here, okay? So 2 over 4x to the 4th plus x. Okay, we had 2 over 4t to the 4th plus t, but now we've got 4x to the 4th plus x. Okay, so in the second one right here, here's another question. Find the derivative of g of r. So g prime of r is going to equal the square root, and I just plug r in for x right here, and this is the derivative with respect to r. So it's really, really that simple. Simply plug in that upper boundary. Now here's the thing that we have to realize, and this is the only time this is going to work. When we identify f of x as the integral from a constant to a variable. So that is the situation that has to be in play when we're looking at these problems. One of the things that catches us is when this top integral isn't just an x. Like in this case, we have f of x equal to the integral from 1 to x squared of cosine t dt. So we said that in order to find this derivative, we're just going to replace the t's with what's up here, right? Well, in that case, it would give us cosine of x squared. The problem comes in, though, when we take this derivative, there is a chain rule episode that goes on. So I need to multiply this by the derivative of that upper boundary. Okay, so when we say the derivative of f of x is cosine x squared, we have to multiply by the derivative of x squared, which is 2x. And you can see that played out here again in question, the second one right here, the integral from 1 to x cubed of sine t dt. So that's going to give us sine of x to the third, but we have to multiply by the derivative of x to the third, which is 3x squared. And that's mirrored down here at the bottom. When both upper and lower limits of integration are variables, okay, we need to split the integral into two parts. So here's what that means. You'll recall one of the properties of the definite integral was that the integral from a to b could be broken into the integral from a to c plus the integral from c to b. Okay? So when we do these problems, we're going to incorporate that concept here just to see if we can't make these problems a little easier. One thing that's going to be a little confusing that may catch you off guard is this, and let me show you. In one problem, we integrate from x to x squared, or something along those lines. What you need to realize is, in order to break that up, we're going to break that up so that we have the integral from x to 0 to x squared. So the thing is, I don't know if my number, if x is a negative value or a positive value. So I'm just going to play it safe, and I'm going to integrate from x to 0 and then from 0 to x squared. All right. So we're putting 0. If I don't do that, right? If I don't take that into account, then I'm going to have the integral from x to some other number, right? And I don't know particularly what that number is. So I'm going to go and say that this is the integral from x to 0 plus the integral from 0 to x squared to account for any numbers that may be negative that I want to plug in for x. Take a look at this one right here. Let f of x equal the integral from x to 4x of t to the fourth dt. So you'll notice we're going to break this integral up into the integral from x to 0 plus the integral from 0 to 4x. All right, that's where that first step is right there. X to the 0, t to the fourth dt plus 0 to 4x, t to the fourth dt. Well, I need to rewrite this first integral so that it looks more like the fundamental theorem of calculus, where we say the integral from a to x of f of t dt, right? Well, in this case, my x and my a are backwards. So there's another property that says you can swap these boundaries if you'll put a negative sign out front. Now I have the integral from 0 to x t to the fourth dt plus the integral from 0 to 4x t to the fourth dt. And I'm ready to go in and find out what that looks like. So our job was to take the derivative of this thing. The derivative of this integral is just going to cancel, right? It's the integral and the derivative cancel and leaves not t to the fourth, but x to the fourth. It's negative because of that negative that's sitting out front. The second one's a little different. So I'm going to plug in 4x for t instead of just x, right? I'm plugging in 4x for t. So that's going to give me 4x to the fourth. But I then have to multiply by the derivative of 4x. The derivative of 4x is 4. So there's some number crunching that's going to go on right here. 4 to the fourth power. I think that's 256. And then we're going to multiply 256 times 4. And that's when we get, what is that? 1,024. Let me double check my numbers here. Just want to make sure I don't tell you something incorrect. So we're going to have 4 to the fourth power. Yeah, that is 256. Times 4 is 1,024. And I'm going to subtract 1, and that's where that 1,023x to the fourth comes in. Yeah, so these problems can be a little tricky if you're not careful. You just have to remember that chain rule concept. Here's one where we do this again, but we're using trig functions to do that. So I'm going to integrate from x to 0, right? Both of my boundaries are variables, so I integrate from x to 0 of sine t dt plus 0 to x squared sine t dt. And then I'm going to swap this around, right, just like I did last time, so that I have my constant on the bottom and the variable up top. So that requires that negative out front. And this one's easy. It's just going to be negative sine x plus, now we've got the derivative, right? We're going to plug in x squared for t. Let me put that square in the right place. X squared for t. And then I'm going to multiply this whole thing by the derivative of x squared, which is 2x. So I have 2x sine of x squared minus sine of x. And that's how I do that derivative. So again, the next steps involve getting into Newton, working through some of those problems. As always, reach out, let me know how I can help.